welcome back, everyone. I hope you had a great coffee break. So we're going to hear more about ARM. So Julius, that's your stage, and let's hear about Trusted Firmware.
Okay, thanks. Is this thing on? Or? Okay, great. So hi everyone, I'm Julius, and I work for Google on Chrome OS Firmware. I'm also the coreboot maintainer for ARM architectures. And I also wanted to talk about Trusted Firmware today. So when I signed up for this talk, I actually didn't know that ARM would also be here and talk about Trusted Firmware, so some of this may be a little duplicate. But my main focus for this talk is a broad introduction to people who have no idea what Trusted Firmware is, who maybe know coreboot and don't really know why the two have been, like why coreboot is using Trusted Firmware these days on ARM64 systems. Actually, when I thought about this talk first, my intention was to do just a general coreboot on ARM64 talk. 2 years ago in San Francisco, I already gave a talk about coreboot on ARM32, and this was supposed to be kind of the next iteration of that. But when I looked into this more closely, I realized that on the coreboot side, there's really not a lot of difference between 32 and 64-bit ARM. There's, of course, the ISA is a little different. There's some differences in the details, but for the general coreboot framework, it all pretty much works the same. And the differences compared to x86 coreboot are also pretty much all the same. So if you look at that old talk, most of these things are still true for 64-bit ARM platforms. The one real difference in how coreboot works these days on these platforms is the Trusted Firmware part, so that's why I chose to focus on that. And to start the motivation of why we even need this Trusted Firmware, it actually has to do with the expectations that Linux has to the firmware environment. So this is a little excerpt from the device tree documentation in Linux. The device tree is this thing which is essentially a big table of hardware description that the firmware passes to the kernel so that the kernel knows how that particular hardware is laid out. And as you can see here, this part talks about CPU runtime power management, so turning CPUs off and on to save power. And on ARM32, that part was still optional. On ARM64, it's now required that we have this weird PSCI thing. So in order to figure out what that is and how we get there, how we can support that with our firmware, you have to follow me on a journey through the trust zone. I mostly put this up because I sometimes get the impression that people who don't know the ARM architecture that well just have heard this term trust zone somewhere, but don't really know what it means and think it's this kind of scary thing that runs the evil code that spies on you or the DRM stuff or something. So trying to take some of that fear away, it's really not that complicated, because if you're running open source firmware, essentially you can also run an open source trust zone. It's really just an architectural feature to run code outside of the context of the kernel. So whoever's seen the previous talk, this is a very similar slide, essentially, just telling you what this trust zone stuff is. It's essentially comparable to system management mode on x86, with the difference that system management mode is a really ugly legacy thing, and this is a much nicer and cleaner extension of the existing architecture. So you essentially just take the existing concept of kernel and userland and expand it to another level. So in the same way userland makes system calls to the kernel can make these secure monitor calls to the next exception level up there. And the whole trust zone isn't just the part down there, but it's the whole part on the right side. So it's like a whole separate operating system and userland that can run these trusted applications that are secured from the rest of the operating system. And this barrier is sort of a one-way street. So the secure stuff can still access the non-secure stuff, but not the other way around. And there's also no true memory virtualization on this right side over here. So the secure OS can actually access the secure monitor memory and thus attack the secure monitor, essentially, unless, of course, you have those new architectural features which we just heard about in the previous talk. And the reason of that secure monitor down there is essentially to arbitrate between these trusted applications that run your DRM stuff or whatever you want them to run, and the main operating system. And that's why it's at the highest It's called exception level in ARM64, but that essentially also means privilege level. So user land is level 0, kernel is level 1, hypervisor is level 2, and then the secure monitor is the most privileged thing at level 3. And the definition of this memory barrier is actually very completely SoC specific. So there's no architectural way in the ARM architecture to say which parts are secure memory and which parts are non-secure memory. Every SoC has its own thing for that. And usually it's just some sort of range register where you say, okay, starting from this offset for this size, that memory area is part of secure memory. And it's not just memory, it's the whole physical address space, actually. So also all the MMIO peripherals, you can say that they only belong to the secure world, and then the non-secure world cannot access that particular I2C controller or something like that. If we want to figure out why we need this to support Linux, we got to again go to the CPU power management stuff. So if you, in case you know, in Linux, CPU power management called CPU idles, essentially turning off a CPU when you don't need it to save power. And if you ignore this slide for a second, on ARM32, this was completely handled within Linux. So when Linux decides it doesn't want to use the CPU, then it turns the CPU off, turns all the power rails off that go to it, and runs the wait for interrupt instruction on that CPU. And then when the CPU wakes back up, it comes back right into Linux, and Linux does all the reinitialization for that. The problem is if you have this trust zone on the side, you can't really do that because the trust zone also needs the CPU, right? So first of all, you need something, when Linux decides I don't want the CPU right now, then you need something else to ask the secure part if it also doesn't need the CPU right now. Maybe you need to keep the CPU alive because the secure part still needs it. And the other thing is, so if you turn the CPU completely off and then turn it back on, then it has lost all its state, of course. And some of that state is not accessible to the kernel. For example, the page table base address register, there's one for the kernel, but there's a separate one for the for the secure monitor. And of course, the kernel cannot write the page table base address of the secure monitor because that would violate the security model. So in order to reinitialize the CPU after it was completely off, those parts that belong to the secure monitor also have to be reinitialized by the secure monitor. And that's why every CPU on, off and on cycle essentially has to go all the way through the secure monitor and back down to the kernel. And ARM has defined an interface, a standardized interface for this called PSCI, Power State Coordination Interface, which builds upon these secure monitor calls, which are essentially like system calls, just going to the secure monitor exception level. And now you could ask, so one interesting thing is that this trust zone architecture already existed on ARM32. It was sort of bolted on in some of the later stages of the iterations of the architecture. But you could also have it there, and you would already have the same problems there. But the thing is, since this evolved alongside Linux, Linux always supported systems that just didn't choose to use it. And in coreboot, we just never really had a need for secure OS or secure applications, and that's why we just ignored it and used Linux ability to work without that. But for ARM64, Linux essentially decided to have a clean break, and now they say all the systems are going to have this trust zone stuff anyway, so we can just rely on it being there, and we don't need to implement all this CPU power management ourselves anymore. So the real reason why ARM64 devices need to provide this PSCI stuff now is essentially because Linux just got lazy and they just decided they don't want to implement the CPU power management themselves anymore. So now we got to give this to them in order to host the full Linux platform, even if we don't want to use the secure part. Now we could implement all of this ourselves in coreboot, but before we do all that work, let's maybe look around to see what other options there are. So what is this trusted firmware thing anyway? For those of you who've been in the previous talk already, most of this is the same. It's a full firmware stack. It's sort of a reference implementation by ARM for all the firmware you need, both booting and runtime firmware. And if we look from the coreboot point of view, coreboot is already the boot firmware essentially, so we don't need that part, but we are really interested in this runtime part. Thankfully, trusted firmware is already split out into these separate stages. And the one called BL31 is the one that really interests us, because that is the part where all this runtime power management stuff is hosted. That is the secure monitor that needs to stay resident across the whole lifetime of the system. And if we compare it with what coreboot already has, it has a bunch of these nice features that coreboot traditionally didn't provide. For example, right now on coreboot, in the ARM architectures, we have no multiprocessing support at all. We just use the one CPU core we boot with and do everything with that, which makes it really nice and easy for us. But of course, if you want to provide these services that turn CPUs off and on, you need to do some multiprocessing, you need to handle coherency and mutexing and all that sort of stuff. It also has a lot of nice CPU core support. So for every CPU core that ARM releases, A53, A57, A70, whatever they're called, all of these have a lot of their own little quirks, and they have the little erratas that you need to support. So it's really nice to have a code base where the CPU vendor itself already programmed all of that stuff, so that you can just use it for them. You don't have to keep up with all the new errata as they come out, essentially. Actually, more than once on one of our existing ARM systems, I've just booted up a new version of Trusted Firmware, and then it told me in some log message, hey, there's this new errata I found that your CPU is susceptible to. So it's kind of nice to get this thing from the CPU vendors who know what they're doing and don't have to do it yourself. If we compare this Trusted Firmware architecture with coreboot more closely, we can see that it's matching up pretty well. So the BL1 and BL2 part are the pure boot firmware part of Trusted Firmware, which is essentially equivalent to the 3 stages of coreboot that we know. And then the BL32 and BL33 are actually not part of Trusted Firmware. It's just names Trusted Firmware gives to the other stuff that it loads. And it's therefore equivalent to the coreboot payload, which is also not part of coreboot, but it's a bootloader that is run after coreboot is finished, essentially. So if we want a secure monitor on coreboot, we really don't need to care about all this other stuff. We can throw all of that away. All we want is the secure monitor part. It would be really nice if we could just yank it out of there and smash it in over here, which is essentially exactly what we did. So we integrate Trusted Firmware as a Git submodule into coreboot. So when you check out the coreboot source tree, you automatically have the Trusted Firmware source tree there as well and can develop on it. And when you build coreboot, it also builds Trusted Firmware and then picks the right part that BL31 out of it and integrates it into coreboot at the right place. So it all works out pretty nicely. And if you're curious about the details of how this is implemented in coreboot, the nice part about coreboot is that most of it is architecture independent, right? So all this logic about figuring out, for example, where this payload is and how to load it and put it in place, that's all independent of the architecture, and we don't need to touch that. The only thing we are touching is really the very last part of the RAM stage where it jumps to the payload. That's an architecture-specific callback. And all we do for Trusted Firmware there is essentially we're saying, if we're running Trusted Firmware, then instead of jumping to the payload, wait a second, let's load this other thing over here first and run it. And then we pass Trusted Firmware the information of how to jump to the payload. And the payload is already loaded, so the nice thing is Trusted Firmware doesn't really need to know anything about how to access the flash or something like that in these architectures. The payload, like the next stage is already loaded, and we just tell it how to move on after it's done its thing, essentially. This is a quick overview about how the Trusted Firmware repository is laid out. So my goal here is essentially to give you a rough idea of where to look if you have to implement your own SoC for like if you're implementing an SoC in coreboot and want the Trusted Firmware support to get it working on ARM64. This is just a small excerpt of the directories there. A lot of these, like I left the ones out that you don't need to care about, essentially, if you only care about coreboot. So next to the BL31 directory, there's also a BL2 and a BL1. You can just ignore those because we are not using those. There's a lot of really good documentation. So if you're trying to work on Trusted Firmware, my recommendation is really to look at those because they're great, especially this porting guide is essentially your one-shop stop for implementing a new platform. It tells you all the macros you need to define, all the functions you need to implement, and so on. If you're looking for drivers, they're all sorted by vendor. So if you're looking for the generic interrupt controller, for example, that most SoCs use, that is under ARM. If you're looking for a standard 16550 UART, which most SoCs use, that is under TI in this case. But most of the drivers that cannot be reused between SoCs are just in the platform part over here. So actually a lot of the framework is pretty lean, and a lot of the stuff is just implemented in the platform, and every platform does it however it thinks it wants to. One of the few things that you still have generic for all platforms to use, the CPU stuff is pretty great. So as I said, they have all the CPUs already implemented, and you essentially just need to add the right CPUs that your SoC has in the makefile. and then it builds them, and then it can automatically detect which CPU is which. So when it brings up a CPU, it reads the identification register and searches for all the CPUs you compiled in, which one this is and which code to use for that. And yeah, as I said in the platform, first of all, there's a common platform directory. So there's a lot of callbacks for things which the platform can change if it wants to, but usually most platforms just want to do the one thing that makes sense to most of them. So there's a bunch of stuff implemented in common that you can just link in because it will probably work for you. And then every platform does its own thing. There's usually a plat setup thing that is the first thing that runs during boot and does all the boot initialization. There's a PM thing usually that implements those pesky callbacks, and a lot of vendors sort of factor out some of the common stuff and then the per SoC stuff. And in the end, each platform has a makefile that defines all it does essentially. So there's no complicated configuration framework here. It's not using kconfig or anything. All the compile time configuration options you have are just options in the makefile, and then essentially which drivers you link in the makefile. So if you want to support a new platform for coreboot, the one thing you really need to implement is this pesky stuff. So let's look into that for a bit. And the main message here is essentially it's very flexible. You can do whatever you want, whatever is best for your SoC. So each of the things that you can turn on and off essentially for runtime power management, you have these nodes at the bottom, which are in a hierarchy of power levels. And in the bottom level, you always have the CPU, or in case of multi-threading, that would be the threads actually. And then you can have as many layers above that as you want. You don't need to have any layers, but most SoCs have their CPUs in some sort of cluster. And when you turn off all the CPU in a cluster, then you can turn off some extra stuff for the cluster. So this power level stuff allows you to build the topology of your SoC in the framework essentially. And you just tell it which maximum power level you want to have, and then it handles all the stuff of calling the right functions for each power level to turn them on and off, for example. And orthogonal to that, you also have power states. So there's not just on and off. There can be as many as you want in between to have a trade-off between exit latency usually and power draw. So rather than just turning it off, you can maybe put it into a retention state that you can wake up from quickly. And there again, you can have as many states as you want. You can define all of that inside your platform. The only thing you tell the outside framework is whether this is an off state or a retention state. The difference there is that in the off state, it loses all its state, and you have to, like, the framework will reinitialize all of the state for you when it comes back up. In the retention state, it's expected to keep that. And then the only thing you really need to implement once you've decided how this hierarchy looks is a structure full of function pointers, essentially, which with all the callbacks for how do I turn off the CPU, or any of these nodes, actually not just CPUs, how do I turn it back on, what do I do with it after it's turned back on, so that is this finish callback down here. And there's a bunch more, but the general gist of it is this, that you just have this bunch of functions you need to implement, and then the framework knows how to call it correctly. So that's really all you need for the pesky stuff. And once again, the documents are really great to look into how this works in specifics. And also, of course, just look at existing platforms. My favorite is always the Rockchip one, because their SoCs tend to be really simple. They don't have any of the weird hooks and crannies that some of the other more complicated SoCs have. So they usually make a good example. Once you have that, you're essentially done supporting coreboot, but you can do some more stuff if you want to. So one of the common things you might want to do is custom SMCs. Of course, this pesky also uses SMCs, and all of those are already implemented in the framework, so you don't need to worry about those, but you can add your own if you want to. Common thing that we need, find that we need is runtime DDR frequency scaling, for example, because if you do anything that involves memory, since memory is used by the whole platform, usually it needs to go through the highest privilege level to allow that. And it's also pretty simple. They essentially have a macro that you can use to define a handler for a given range of SMC function IDs. There's actually this whole big specification from ARM that tells you which SMC function ID ranges are allowed to be used by whom. Usually the one you want to use is called the SIP range. I always forget what it stands for, but it's essentially the SoC vendor range. So if you're implementing an SoC port, that's usually the one you want to use. And last but not least, we have some fun coreboot support in there now. One of the problems with integrating coreboot is that there's not yet a great way to pass parameters in a generic way from coreboot into Trusted Firmware. This is something that I think the Trusted Firmware team is interested in making better in the future. But right now, all that they have is essentially you can have one pointer of platform-specific information, and then the platform has to figure out how to deal with that. So the first piece of platform code that's called when you are in Trusted Firmware is usually the function over there, which gets that one pointer, and then you have to figure out what to do with that. Usually we find that we have to pass a bunch of things from coreboot into Trusted Firmware. So what we do is we build a sort of primitive linked list with that and then parse it when like at the very first thing in Trusted Firmware. And one of the things you should pass is the coreboot table base address, because then you can use this coreboot table setup function, which we have in Trusted Firmware, which gives you all the coreboot, the generic coreboot support that we implemented, which is right now mostly console support. So, for example, after that, you have access to the console, the UART information over there. So you don't have to hard code the UART base address anymore. You can use the one from coreboot. And more importantly, you essentially take over coreboot's configuration with that. So if you disable the UART in coreboot kconfig, then it would just not pass that, and then Trusted Firmware will also not use it, which is nicer than having to disable stuff in every different repository your firmware is made of. The other nice thing you get with this automatically is CBMEM console support. So as soon as you, like if you have a CBMEM console in coreboot, then information about that is passed in the coreboot table, and then Trusted Firmware will automatically register a console driver for that. And then once you boot into user land, you can dump the CBMEM console and see all the Trusted Firmware logs right after the coreboot logs. I think this is pretty much all I want to talk about the basic Trusted Firmware architecture. The one thing I want to leave you with is a little anecdote about some of the practical problems we had when implementing one of these SoCs in Trusted Firmware. This is about the Rockchip 3399, and well, we essentially had some trouble fitting everything there. The story starts very simple with bringing up the chip and trying to get suspend resume support working. So of course the whole system suspend resume also needs to go through the secure monitor, because it turns off the whole system, so the highest privilege level needs to know about it. And you usually turn on, like the DDR controller usually uses state doing that, so you have to reinitialize it somehow when you come back up, and of course the code for that can't be in DRAM. So thankfully we are an ARM SoC, we usually have a bunch of SRAM, so we can put it in there. Come on. And we have quite a lot of SRAM on this platform, so that's pretty easy to fit. Then we had some other issues about we want to do some DDR frequency scaling at runtime. Depending on the SoC, this is sometimes pretty easy and sometimes a real chore. On this one, it was thankfully not that hard, because we have this little separate microcontroller in the SoC, like a Cortex M0 essentially on the side of the normal CPUs, which had the ability to just stop the CPUs in place, retrain DDR to a different frequency, and then kick them off again. The main CPUs never really knew what did them. So this was pretty easy to implement, but we still needed to put some code in. Like we needed to host that code for this M0 in SRAM, of course, because DDR isn't accessible while we're changing frequencies. And we had some more fun with trying to work around hardware bugs. So this SoC had a particular thing where when it goes into system suspend and it gets a wake interrupt at just the right time, like just after you turned off the main CPU, then sometimes it wouldn't wake up again. So to work around that, you essentially needed something to sit around and wait until after all the CPUs have been turned off and check for this condition and then clear it. So here comes our M0 to the rescue again, and we had to implement some code for that. All of this still fit pretty nicely into SRAM, but then we had a great idea on how to save some more power. Right, this is where I want to be, which is essentially, there was one more power rail we could turn off, which powered most of the chip, and turning it off would have saved us really a bunch of power. Unfortunately, it also powered the SRAM. So at that point, we sort of have a problem, because we can turn the system off, but when we turn it back on, we don't have anything to resume from. So the one good thing we had was we have this little amount of PMU SRAM, which is sort of a separate amount of SRAM that's implemented, that's powered by a different power rail, and would stay alive even if we turn this off. But now we have to start fitting all of this stuff in there, which is kind of awful. The DDR init stuff still kind of fits. One of the problems that we also have here is that the entry point of the CPU when it comes back from resume, you can essentially only give the SoC the top 16 bits, so it has to be 64K aligned. Thankfully, the PMU SRAM is 64K aligned, but it needs to sit at the very top for that. And the M0 code also needs to be 4K aligned, because that's how the M0 works. So first of all, putting the whole M0 code that we have right now in there doesn't fit at all. There's no way. So our idea was, rather than having one M0 image and giving it an argument of which of the two functions it's supposed to do, we could split it up and have two M0 images and then just always give the M0 base address for the one we want to use when we kick it off. This sort of works, but if you can see between these two, it overlaps part of the DDR and its stuff, so it doesn't quite fit. And it needs to be in the middle there because it needs to be 4K aligned. So this also didn't quite work. But then we realized the DDR in it has to start at 64K, but after that it's really just normal code. So we can really sort of rip it apart and sandwich it carefully around the M0 code. And come on. With a lot of, juggling bits and counting instructions, we managed to get this all in 8K. You have one problem left if you do all this, which is that since you lose SRAM and S3, of course, you lose that DDR frequency scaling stuff. So it would be not that great if DDR frequency scaling worked after you boot it, but then once you suspend resume once, it doesn't work anymore. So the ugly but obvious solution is to cache it in DRAM. I think this thing is dying there. And then just copy it back every time we resume, essentially. So if you want to look how this madness looks in a linker script, I got it over here. Can we switch the slides manually? Thanks. So the ink bin stuff is essentially the M0 code, so you see it needs to be 64K aligned. And then even though the other stuff is the same program, if we put the data section beyond that, it just happens to magically work out, and we're just hoping that we never have a compiler change or anything that messes all of this up again, because it's going to be the most awful thing. If you want to see some details about how you do this sort of thing, where you build the binary for a completely different chip inside the same software as the main, like inside your main software package, and link it all together, it's somehow done like this. So first of all, like you essentially first build that M0 code completely separate into a stripped binary, and then you would define a makefile rule for the main software where that binary is another dependency for the for one of the C files, and you also pass the name of that binary in as a preprocessor macro. And then you can use this weird assembly instruction called inkbin, which essentially just tells the assembler to, at this point, include a whole other file completely and then continue assembling. And then you put a label around of it, and then you can access it from C code and tell the M0 base address, which is to just put the address in there and then sort of work out. And this is the M0 code we run on suspend in the end. As you can see, it's really simple and really stupid. There's essentially this suspend state, which keeps counting upwards as you go through the suspend, and then again as you go through the resume later. As you can see, we had some other issues we also had to work around in the end. Like as you keep testing more and more on the platform, you keep finding more things. This is actually where the system is suspended in here. So if you take one of these Chromebooks today and you close the lid, then even though it's supposed to save power, the whole time where the lid is closed, you have this little Cortex M0 saying in a tight loop, am I already resumed? Am I already resumed? Am I already resumed? But it turns out that M0s don't eat a lot of power. And if you do that on a 32 kilohertz clock, it's actually not as crazy as it sounds. You just shouldn't know how the sausage is made in that case. Yeah, that's all I have. So thanks for listening. Does anyone have any questions?
All right, thanks so far. Questions?
Why does the DDR3 controller need to be reinitialized after S3 resume? Why, for instance, can the hardware put that in self-refresh and at boots it works basically?
Right, so this is not the DDR itself, right? So the DDR chip on the board is put into self-refresh, but the DDR controller on the SoC needs to know how to talk to the DDR, and that part isn't maintained mostly to save power. So we shut off most parts of the SoC when we go into S3, and that's one of the parts we shut off. So after the boot, you need something to tell the DDR controller how the DDR chip, like how many rows, banks, and columns, and so on you have, and to tell it to take the DDR out of self-refresh, and all that kind of code needs to live somewhere.
And second question, why don't you do the initialization part like a normal boot like in coreboot on x86?
Are you asking why we're not reading it from flash, or?
Yes, why aren't you doing it dynamically from code that is in flash?
Right.
Not necessarily saving data on flash, but...
You can do that. It sort of depends on the SoC. So this SoC in particular, I think, was designed to resume from SRAM. So I'm not sure if starting the boot ROM again from flash would even be possible. Okay. The other reason you might not want that is it sort of depends on how your system is designed. In our case, this is a Chromebook. So Chromebooks are always designed in a way to boot from a read-only partition and then do some crypto magic before we jump into the partition we can actually update on the flash. And we found out in the past that tying the resume path to this read-only flash is a very bad idea, because that means that if you ever have a problem in your resume path, in your early resume path, you can't really fix it. So resuming from SRAM is very nice, because then you can always update it, and you're not bound to the stuff you have put on flash, essentially.
More questions?
Yep.
Sorry, going back to one of your very going back to one of your earlier slides, you've replaced the early stages of trusted firmware with coreboot code. I'm not a trusted firmware architect or expert, but I'm sure it would alarm those who are, because the whole root of trust derives from the early stages of the trusted firmware.
Right. I mean, so it always depends on what you want to do with the system, right? So trusted firmware has many things it does and many use cases. They do have a system of trusted boot where every stage verifies the next, but of course you don't have to use that. In this case, the goal was essentially to get coreboot working on ARM64, and what we needed was a secure monitor. So we just took the secure monitor that existed and didn't really care about the other things. If you want trusted boot, coreboot has its own way of trusted boot, which is derived from the way that Chrome OS initially did it, which is called verified boot, vboot. And the BL31 in this case is part of that. So the way the coreboot way works is you boot from a read-only partition of the flash, you verify the read-write partition of the flash, and then you boot from there. And trusted firmware is just one of the different components that are stored in this read-write partition. So we have our own trusted boot mechanism essentially, and we're just using a component of trusted firmware in there.
Thank you.
So if you had like the ability to tell the SOC guys here how to redesign their SRAM, would you just say don't turn off the SRAM, or did you like having the two partitions for power reasons, or what's your feeling on that?
I'm not a power guy, so I don't know how much SRAM itself actually takes. I think in this case it was sort of a design problem of just tying everything to this one big power rail. So if you turn that off, it was really other components that we wanted to turn off, but the SRAM just happened to also hang on there. So it would probably be better to put SRAM on a separate rail, or put it on an always-on rail, essentially, that's supposed to stay alive. But the problem is, what we did on this chip is essentially something that the chip wasn't really designed for. We just figured out afterwards, hey, this is something we could, in theory, turn off, maybe if we just do it right. I also think the idea of having split SRAM is not that bad. So 8K is unfortunately not that much. So having something like 16K, 32K would be much easier to work with, and then maybe that's good enough, and you can turn off the main SRAM.
What kind of information are you passing from coreboot to the firmware?
So the coreboot table base address for one. The other things that we usually pass is some information specific to the board. So we had this design philosophy when doing this to try to not pull board-specific information into trusted firmware, because Most of the stuff Trusted Firmware deals with is only specific to the SoC, so how to turn off CPUs on and off. It doesn't really care about the rest of the components on the board. And if we had a notion of the board in Trusted Firmware, essentially it would make the whole thing way more complicated, because every board that we implement with that SoC would have its own code in there, and it would just become more complicated. So what we decided to do is, in those few cases where the Trusted Firmware needs to know something about the board, this is, for example, when it wants to reboot, it needs a way to reboot, and on some systems we reboot through an external GPIO, on others we use some SoC internal mechanism. So in that case, we would have a parameter that tells Trusted Firmware which reboot mechanism to use, and that way we can tell it board-specific information and don't need to hard-code board-specific code in there.
Okay, I'm just telling you because now in the firmware we support dynamic configuration, which basically consists on passing a device tree between images. So maybe this is something that you could use in the future.
Right. Yeah, I've heard about that. I wasn't sure that if it's finished yet or not, but it's definitely something we'll look into. For the next
I'm not sure
platform.
how it would work in your case with skipping the first stages of the firmware, but yeah, I'm sure it could work. And we are already using it in some reference code for passing arguments between images to, for example, share memory between different images.
Okay.
So yeah, I'm pretty sure it could work as to pass addresses for a peripheral or something.
So is it an interface between BL2 and BL3.1, or?
Right now, as far as I know, we are using it between BL1 and BL2, but there's no reason why we couldn't use it in BL3.1.
Right. So I think that is the extension, essentially, that we are still waiting on before we can skip to a better mechanism. Yeah.
Hi, what's the boot time penalty now that you have to use ARM Trusted Firmware?
It's usually not that bad, because it doesn't do a lot during boot. It just sets up. So Trusted Firmware is not supposed to do any SoC initialization. We have all of that in coreboot. So really all it does on boot is setting up its own stuff and then passing on to the next part. And it's really only meant to do these runtime services. So it's usually below 15 milliseconds to go through the Trusted Firmware part.
Yep. Just out of curiosity, I think on that rack chip platform there was a dedicated microcontroller for the DRAM suspend stuff. The DCF. Can you tell us the story about that and why it was replaced by the N0?
Yeah, I don't think I can remember all the details. The DCF was this thing that they implemented specifically to do the frequency switching, and it was like their own little microcontroller with only a couple of instructions, and really crazy thing essentially that, like, we didn't have an assembler for that. We had to ask them for code for it, and I don't really remember the details, but at some point essentially we found something that we needed to do during the frequency scaling that we couldn't with the DCF, and then we thought, why are we doing this if we just have a full ARM core there that can do everything and is fully general purpose? So we switched to using that.
Oh, we still have room for another 2 questions, maybe?
In terms of whether to use the, like, you pulled the one part out, and then the question was, what about those earlier parts? Do you know their policy on booting versus bricking? In other words, the coreboot thing is it'll always come up and it'll just tell you things didn't go well. But do you know what the ARM stuff does? In that case, I'm just curious.
I'm not really familiar, honestly, with those other 2 parts.
Okay.
But the thing is that I think it's a very thin framework, so a lot of the stuff is left to the platform, and the platform is supposed to figure those kinds of things out, like what happens if it fails or something. I think the actual generic framework parts for BL1 and BL2 are very, very lightweight and don't really do that much.
All right. If there are no more questions, then thanks
you very
again
much.
very much, Julius.